Hello everyone, welcome back to my channel. My name is Chinmaya Shetty from Sri Venkateswara College of Engineering, Bangalore, from the branch of Information Science and Engineering. Today I am going to tell about optimal binary search trees. Optimal binary search trees are a type of binary search tree that minimize the expected search time. They are used when the search probabilities for different keys are known. The goal is to construct a tree that minimizes the weighted average of the search cost. Basic concepts of binary search tree. It is a binary tree where each node has a key and the left child has a smaller key while the right child has a larger key. The search cost of a key is the number of comparisons needed to find it. The optimal binary search tree has the minimum expected search cost. Dynamic programming approach. Dynamic programming is used to solve the problem of constructing an optimal binary search tree. The algorithm computes the expected search cost for each subtree and uses these values to build the optimal tree. It works bottom up, starting with the smaller subproblems and using their solutions to solve larger subproblems. Optimal substructure property. Optimal binary search trees exhibited the optimal substructure property. This means that an optimal solution to the problem contains optimal solutions to subproblems. By leveraging this property, dynamic programming can efficiently solve the problem. Computing the expected search cost. The expected search cost of a subtree depends on the probabilities of searching for each key in the subtree. These probabilities can be pre-computed and stored in a matrix. The algorithm uses the matrix to compute the expected search cost for each subtree. Building the optimal tree. Once the expected search costs are computed, the algorithm constructs the optimal binary search tree. It uses a separate matrix to keep track of the root of each subtree. The root matrix is used to reconstruct the tree recursively. Computing expected search costs. We start by computing the expected search cost for each individual key and dummy key. The expected search cost for each key is the probability multiplied by the depth in the tree. The expected search cost for each dummy key is the probability multiplied by the depth in the tree plus 1. Constructing the root matrix. The root matrix is to keep track of the root of each subtree. The root matrix is filled bottom up, starting with the smallest subproblems. It stores the index of the root node with the minimum expected search cost. Reconstructing the optimal tree. With the root matrix computed, we can reconstruct the optimal binary search tree. We start with the root of the entire tree, which is stored in the top right entry of the root matrix. We recursively construct the left and right subtrees using the roots stored in the root matrix. Example of optimal tree. Using the computed root matrix, we can construct the optimal binary search tree for our example problem. First thing, sorting. Sort the keys based on their probabilities in ascending order. The sorted keys are 2, 1, 5, 3, 4. Corresponding probabilities are 0.1, 0.2, 0.2, 0.4 and 0.1. Constructing the optimal binary search tree. The goal is to construct a binary search tree with the sorted keys such that the expected search cost is minimized. To achieve this, we can use a dynamic programming approach. Create a 2D table cost where cost of I of j represents the cost of the optimal binary search tree for keys I through j. Create a 2D table root where root of I and j represents the root of the optimal binary search tree for keys I through j. Initialize the base cases means single key trees in the cost and root tables. Fill in the tables using a bottom-up approach, considering all possible subtrees. The final cost and root tables will help us construct the optimal binary search tree. Result: the cost and root tables will guide us in constructing the optimal binary search tree. The root of the entire tree is given by root of 1 and n, where n is the number of keys. Visualizing the optimal binary search tree. With the information from the root table, we can construct the optimal binary search tree. The tree will be constructed or structured such that the keys with the higher probabilities are closer to the root. Applications. Optimal binary search trees have various applications including language modeling, information retrieval, and compiler optimization. They are commonly used in scenarios where efficient search is critical. By minimizing the expected search cost, they improve the overall performance of search operations. Limitations. Optimal binary search trees assume that the search probabilities are known in advance. If the probabilities change frequently, the tree may no longer be optimal. The algorithm also assumes that the search costs are symmetric, means the cost of searching for a key is the same as searching for its associated value. Advantages. Optimal binary search trees guarantee the minimum expected search cost. They provide an efficient solution to the problem of constructing a binary search tree with the known as search probabilities. By minimizing search time, they improve the performance of search operations. The algorithm for constructing an optimal binary search tree is based on dynamic programming. This approach breaks down the problem into smaller subproblems, solving them recursively and storing the solutions to avoid redundant calculations. This contributes to the efficiency of constructing optimal trees. Disadvantages. Optimal binary search trees requires prior knowledge of search probabilities. If the probabilities are unknown or change frequently, the tree may not remain optimal. While optimal binary search trees optimize the average search cost, they do not guarantee the best or worst case performance. In scenarios where worst case performance is critical, other data structures like balanced binary search trees or hash tables might be more appropriate. Implementing the dynamic programming algorithm for constructing optimal binary search trees can be complex and may require a good understanding of the underlying principles. This complexity could be a drawback for developers seeking simpler solutions for their specific applications. Conclusion: optimal binary search trees are a powerful tool for minimizing the expected search cost. They leverage dynamic programming to efficiently construct a tree with known search probabilities. By carefully selecting the root of each subtree, the algorithm guarantees the minimum expected search time. Thank you.